Good afternoon and welcome to the University of Manitoba Alumni and Friends Virtual Learning for Life Program Climate Series. My name is Tracy Bowman and I'm the Executive Director of Alumni Relations and a proud alum. Before we begin, I'd like to acknowledge that the University of Manitoba campuses are located on the original lands of the Anishinaabe, Cree, Oji-Cree, Dakota, and Dene peoples, and on the homeland of the Métis Nation. We respect the treaties that were made on these territories. We acknowledge the harms and mistakes of the past, and we dedicate ourselves to move forward in partnership with Indigenous communities in a spirit of reconciliation and collaboration. Thank you to all of us for joining us and making this event a part of your day wherever you are joining us around the world. We are able to offer this program free to all of our alumni and friends thanks to the very generous sponsorship of our affinity partner, IA Financial Group. Many thanks to them. You can learn more about the insurance options that they offer you alumni on our alumni website. So before we get started, just a few housekeeping details. So if you've been with us before, this is old hat, you'll know all of these things. We are recording today's session so that we're able to share it with you later on. We post it on our YouTube channel so you can watch it again and again and share with friends and family around the world. We will send you that link in a day or so afterwards, as well as a follow-up survey to gather your feedback. If you would like to ask questions of our presenter today, we have two methods that you can do that with. The first one is the platform Slido. That's www.slido.com. And today's password is VLFL27. The other method is you can use YouTube right here where you're watching it, just in the chat function, and we're able to post those as well. So I will go back and forth between Slido and YouTube and ask as many of your questions as possible. We'll try to get through them all. So I do encourage you to ask away and start asking those questions during the presentation. So then we're ready to go as soon as our presenter's done. So now let me introduce today's presenter. We have Dr. Juliana Marini Marson, and the topic she'll be presenting today is Virtual Planet Earth. Can we trust models to predict changes in the climate system? So let me tell you a little bit about her. Dr. Marini Marson is an assistant professor at the University of Manitoba's Department of Environment and Geography, and is also a researcher at the Center for Earth Observation Science, or CEOS, as we call it. Her research focuses on the polar oceans and their interactions with the cryosphere and climate. In particular, she uses numerical models to understand how warming and increasing freshwater input to the polar and subpolar oceans can change their physical and biogeochemical characteristics. Dr. Marini Marson is fascinated by icebergs, their role in ocean dynamics and primary productivity, their patterns of drift, and how they can affect marine transportation and other offshore activities. She is specialized in iceberg modeling, and parts of her scientific efforts are dedicated to improving the numerical representation of icebergs so we can better predict their environmental impacts and trajectories. So with that, I'm going to pass it over to you, Dr. Marini Marson.
Thank you so much, Tracy, and thank you for the introduction. Actually, that helps me a lot during my presentation. Everyone will know why I'm talking about what I'm talking about, right? So, hello everyone. Good afternoon. So I think you all have heard about the IPCC and their reports, right? So we had a new report that came out last year and this year from the IPCC, the International Panel on Climate Change, right? And the IPCC, what they do is that they will give you an idea of how the climate is predicted to change in the future. And the way they do that, of course, they use a whole bunch of data, but they also use a series of numerical models to do that prediction. So those models are the type of models I'm going to talk about today. But before I start talking about the models, there we go. I'm just going to briefly introduce myself a little bit more personally than what Tracy had there. But so I'm originally from Brazil, from a small town the state of São Paulo. You can see from the pin there. And I got all my degrees from different parts of the country, starting with my bachelor in oceanography and then specializing in physical oceanography. And as a physical oceanographer, I'm very interested in the characteristics of the ocean, such as temperature, salinity, their distribution, and also the dynamics of the ocean. For example, studying currents in the ocean, right? So in this little globe here, what you can see is the temperatures of the surface of the ocean are shown in colors there. And this is the type of thing I would be looking at in my daily work life. And although I could have focused my research around the tropical oceans, which are closer to home, right? My heart set on a much further and colder place, right? So I'm very interested in the polar regions. So when I began, I was a field oceanographer. I went to the Southern Ocean to take measurements from the ocean every summer, and then came back, analyzed those observations, and did my analysis on those. But then I became a modeler, and things now look like this. It's a lot less exotic than before, but to me, at least, it's as exciting as it was before. So I may be shooting myself in the foot right now, but I want to start with this. All models are wrong. The practical question is, how wrong do they have to be not to be useful? So my hope is that by the end of this talk, you will understand this quote and also appreciate the usefulness of numerical models. All right, so here's an outline of this talk. I will first define what a model is. Then I'm going to show how the models have evolved until now. We are going to discuss if we can trust models. I'm also going to point out some of the missing points in models, or missing things in models. And I'm also going to talk a little bit more about my work and how do I fit in this scenario. Okay, so what is a model? Simply put, a model is a representation of something, right? And this representation is very useful for us to understand better how a system works. And it is also useful for us to predict changes within that system. Now, of course, we need to have a decent understanding of the system in order to give a good prediction of those changes. Now, models are basically divided into three types. We have physical models, we have conceptual models, and finally we have the mathematical models. Physical models, as the name suggests, are physical representations of a system. So that's when you build something like this, for example. They are studying the influence of jetties on navigation. So you would have that in a sort of a miniature of the replication of the environment itself. Then the conceptual models are those schematics, let's say, that where you have all the elements that are important within that system. And all the arrows there are representing the exchanges between the elements. So how do they exchange mass, momentum, and energy? And conceptual models are very useful for us to actually be able to build mathematical models, which is the last one that I'm going to talk about, and is actually the type of model that I work with and that I'm going to talk about today. So, sorry, I jumped the gun there. So mathematical models are consist of sets of equations that usually represent conservation laws, for example, conservation of mass, momentum, and energy, right? So it's a set of equations. So I want to give an example by going back to your fond memories of your physics classes in high school. And now I can show this, and you probably will recognize this as Newton's second law, which tells us that the sum of forces in a body that are applied to a body is equals to its mass times the acceleration of the body, right? So that's also known as the conservation of momentum equation. If you had some calculus in the past, you're also going to recognize this little thing here, which is a derivative. And what I did is just, I'm writing exactly the same thing, but I'm describing the acceleration as the rate of variation in the body's velocity with time. That's what this means, right? And if this time interval that I'm considering is very, very small, I can also write this expression in this way, okay? So in this case here, what I'm doing is transforming this derivative here in a discrete operator, which is this part here, where I just subtract the velocity, the initial velocity from the velocity that the body will have in the future, divided by that time interval, right? So again, if you remember your classes, you would have a question on your exam. And if on that question, I would give you all the forces that are acting on the body, I would give you the mass of that body. I also will give you the initial velocity of the body. And this in modeling, we call as initial conditions. And they are very important to actually solve those set of equations that we have. And I ask you, what is going to be the velocity of the body after a certain amount of time? So this certain amount of time is also provided by the problem, and then you can calculate the V in there, right? So what essentially you're doing here is that you are predicting what will be the velocity of that body in the future. So that's exactly what models do. Well, I wouldn't say exactly. It's a little bit more complicated than that. I have an example of a set of equations that describe the movement and exchange of mass in the ocean. Okay, so don't worry about all this. But what is complicated about it is that some of the forces that I mentioned before also have to be calculated, and sometimes they depend on unknown values. So that turns those equations into nonlinear equations, which means they are very, very hard to solve and impossible actually to solve on their fully form by hand or analytically, as mathematicians like to say. So that's why we need algorithms and computers to actually be able to solve those complete set of equations. But once you solve them, this is what you get. It's a pretty picture of, in this case, what the sea surface temperature will look like at some point in time. This is an output, as we call, from an ocean model. So it's what the model is going to solve that set of equations, and is going to give you the fields of temperature, salinity, velocities that you're looking to know more about. So the same way that we oceanographers have a set of equations that describe the processes in the oceans, sets of equations have also been developed for different components of the climate system, such as, for example, for the atmosphere, for sea ice, for vegetation cover, land surface, land ice, and many other components. Now, one thing that we have to remember is that all those components of the climate system, they are not isolated. They actually interact with each other, and this interaction is super important. So what we do in models is that we also allow those different models, the atmospheric model, the ocean model, the sea ice model, to talk with each other in what we call a coupled model. So those are what they call coupled models. And those coupled models are the ones that are used to make projections of how the climate will look like in a certain amount of time. So here I have just a schematic showing all the interactions between the different components of the environmental system. You have interactions between ocean and the atmosphere, with the soil there, land, with ice. So those coupled models, they allow these sets of equations to calculate their results, but also to pass those results to a neighboring component, so that component can take those results and also take that into account on its own calculations. And then we will allow the model to give you feedbacks between one process and another. So for example, take into consideration sea ice when you're trying to predict how warm the planet will be in a few years. It's super important because there is something that is called the sea ice positive feedback, where when you increase the temperatures in the atmosphere, you melt more sea ice. So where before you had sea ice, which is it's a white surface, right, that reflects lots of energy, now you have ocean that is a lot darker and will absorb lots of radiation. So less sea ice will actually lead to more absorbed radiation, which leads to higher atmospheric temperatures. And the cycle goes on with even less sea ice. So you see, if you isolate those two components, they won't work very well. To actually simulate the whole climate system, you do have to take into account those different components and how they interact between each other. All right, so this is all great, but we have to remember that all those sets of equations, they are based on our best current understanding of how things work in the environment. But again, we don't know everything, right? And sometimes we think we know something, but it's not exactly that. So that's why models are only representations of a system, in this case, the climate system. And that's why we say that they are always wrong, because they are based on our understanding, and our understanding is limited, right? And it will always be that way. I'm pretty sure we will not be able to describe nature in its full sense anytime soon, because just our brains are not going to get there. It's just too complicated. So that's the reason for this part, okay? Models are wrong in the sense it only goes so far as our understanding goes. So how have models evolved until now? Well, the first models that appeared were the atmospheric models. In fact, the framework for weather forecast was already in place in the early 20th century. And the first attempts to actually forecast the weather were done around 1920. And they, of course, were done by hand. So what they did is to simplify that set of equations in a way that they can actually be solved by hand. But of course, that was not very efficient. There is one person that tried that, and to make a forecast for 6 hours ahead, it took him 6 weeks of calculations to get that forecast, and the forecast was wrong. But that was not a problem with the model or the set of equations themselves, but with the initial conditions that were provided by instruments that at the time were not very good. So that small errors in the initial condition were propagated and increased as you move your time in the model, you integrate forward in your model. But anyways, as you can imagine, when computers showed up, then a whole range of possibilities also showed, right? So now not only the atmospheric models were run in computers and actually producing forecasts a little bit faster than doing by hand, but also other sets of equations were being developed to represent other components of the climate system. And with time and with our understanding of how these components interact with each other, and with the increase in computational power, we were able to start coupling those different components. So the oldest coupled system we have is the atmosphere-ocean coupling. So that's a very common type of coupled model that takes into account both atmosphere and ocean. If you move forward in time, the latest addition to climate models now are the ice sheet models. And I'm going to discuss a little bit more about them later on. So not only more components of the climate system started to being coupled, but also more processes inside each of those components started being represented or were represented better with time. So this figure here is from the IPCC's fourth report that came out, I think, in 2007. And one example of how processes can be added or can get more sophisticated with time, for example, is the ocean here first. The ocean was sort of only like a one layer ocean, and now we can actually solve the 3D circulation of oceans in climate models. Additionally, the resolution of models have increased. Resolution is the size of those grid boxes here, or sort of pixel size, right, of the model. And you can see that from the past to 2007, I won't say present, the resolution has increased a lot. So now you can actually see that what you have here is Europe, right? Here was sort of hard to tell. And now your boxes are much, much smaller, and you can solve those set of equations for each one of those little boxes there. That's why you need a whole lot of computational power to do that. Currently, we are in the 6th assessment report for IPCC, and the models that are used in the current report is actually one quarter of resolution of what you see here. So this was the first time that models with resolutions as little as 27 kilometers were included in the IPCC report. Now, can we trust models? I'm gonna start discussing this by showing this this plot here. So this is showing the temperature change in Fahrenheit. Sorry, that was an American that did this, but it's showing the temperature change with respect to the average between 1980 and 1999. And it's the range goes from 1970 to 2020. So the values that are shown here is the actually temperature that occurred on the year minus the average of this period here, 1980 to 99. The red line there is showing the observations. So things that you measure with instruments. And the black line represents an average of outputs from different models. So this what we call an ensemble of models. And what you do is that you just average what they are telling you that is going to happen. So you will have a more robust outcome for them, right? So this is the black line here. Now, the catch here is that this black line, this ensemble mean here, was run in 2004, which means that everything that comes after the dashed line was actually a projection at the time. It was something that didn't happen yet, and the models were telling us that the temperature would change in this way here. And then we went on, and as those years passed, we collected more observations, and that's what is plotted on top of the black line there. And as you can see, the prediction of the model was quite good compared to the red line, right? You have the same trend. They have sort of the same inclination. And also you have sort of the same magnitude. They are, if you imagine an average here for the red curve, they would pretty much line up with the black curve. Now you might wonder about, okay, but this red line is sort of wiggling up and down here, and the black line is not actually following it as well. And that might be for two reasons. One of them is that, as I mentioned, this is an average of lots of results from models. So what might be happening is that some models are doing better on representing those wiggles here, but when you average a whole bunch of different models, you sort of disappear with those wiggles. The second point here is that models are actually not very good at projecting changes in shorter time scales. So let's say from 1 year to another, what's going to happen here? It's a little bit harder to tell. And to explain that, Professor Bruno Tremblay from McGill University once gave me an analogy that is very useful, and I'm going to use it here. So to understand why the model cannot predict this wiggles there, imagine that you are in your car, you're leaving your house at 7 a.m., and you know that you'll be at your workplace at around 8 o'clock. So usually you know that you have to leave at 7 to get at your workplace at 8, more or less, right? Now, if I ask you, where exactly are you going to be at 7:19? Is it here? Or is it there? You probably won't know how to answer that, right? Because it's really hard to predict exactly where in that pathway you're going to be. There might be traffic. There might be flat tire. I don't know. So the circumstances might change, and that might delay, or you might go faster than predicted. So what you do know is that around 8, you'll be in your work. So it's a lot easier for models to predict an average, a long-term thing, than to predict exactly what is going to happen on a small point in time, right? And that's also why we do much better at projecting long-term conditions for the climate than we do for weather forecasting. Most people think that how can you trust climate models if we can even predict the weather, in 3 days? Yeah, there are different things. It's a lot easier to predict this global average long-term trend than those little wiggles that we have here. This is the same graph. Also showing all observations in black and simulations in brown here. Again, this is temperature change in a slightly different time range here. But what I want to show in this graph is that one of the beauties of numerical models is that you can turn on and off different processes and what we call forcings to see how the climate system respond to that. So if we go on our model and we turn the switch off on the human impacts of the climate, the teal line there or the green line is what you get. And what you see is that the model cannot, not even close, simulate this increase in temperature here that was observed just by considering the natural forcings of climate. That means the solar variations, volcanic eruptions, the natural variability of the climate cannot explain the current increase in temperatures, right? So that's how we also use models to detect and attribute changes in the climate system. This is another plot where it shows the correlation between models and observations again. So the closer you are to one, the better your models are at predicting that particular element of the climate system. Okay, the three different colors are for three different phases of CMIP. CMIP stands for Coupled Model Intercomparison Project. So this is where all those models results are gathered together to give you the best estimate of what's going to happen. CMIP 3 came around 2007. CMIP 5 in blue came around 2014. And CMIP 6 is the most recent one. And we got the results on last year, on 2021. So as you move from green to blue to red, you're actually moving forward in time. And what you see in general is that the correlation between the results from those models and the observations is getting closer and closer to one, right? So the models are getting better. Here, if you look at near surface air temperature, is virtually one correlation. So that means that we are really, really good at predicting what the temperature will be in the future, right? Now, if you look at this, for example, this is shortwave radiation that is being reflected back to space. You also see this increase in correlation, but what you also notice is that those little ticks that you have here, those individual ticks, they are individual model results, right? And what you're seeing is that those ticks are more spread in the red one than in the blue or the green one, which means that the models now are giving a larger range of answers than before. And I'm going to talk a little bit more about that on why this is happening in the models. So this is the part where I just try to answer this question. Can we trust models? Yes. Yes, we can, but it really depends on what you're looking at, right? So if you're looking at a process that we still don't quite understand well and or cannot model very well, or these new processes that we are just now starting to model, then you have to be a little bit more careful. But for those well-established processes that we've been modeling for a long, long time, you can be fairly sure that you can trust them. So what are we missing, and what's going on with that model spread that we saw before? This is another graph that also showed that larger spread in CMIP 6 compared to CMIP 5, right? And this is the projected warming in in 2081 to 2100. How many degrees above the pre-industrial values we are going to get at that point in time? What you can see from the CMIP 5 project in 2014 to the one that we got last year is that we are predicting a warmer world in that future, right? So there is this warming here, but also, again, the models are quite spread out, more than on CMIP 5, right? And what people think is going on here is related to clouds. Clouds is cloud formation and representation in models is something that have been problematic for a long time now. It's a very difficult thing to model. And we are trying to improve on that. So the different ways that models are representing clouds in them are actually giving you this large range here in the projections. Is that a bad sign? No, it's good. It means that we're going somewhere with this. Now, if you'll notice the red bar here, that's the IPCC best estimate. And the IPCC not only take into account the results from the models, but they also look at observations and statistics and other lines of evidence, such as paleoclimate records, for example, what happened to climate thousands or millions of years ago. And what they are estimating here is a lot more similar to what CMIP 5 was suggesting than what CMIP 6 is suggesting. So that might make you think that maybe we are getting worse with time, but not necessarily. And that's for two, might be for two reasons. One is that maybe the models in the past were getting correct answers for the wrong reasons. That's something that happens in models. And the other one is that IPCC is usually conservative with their estimates. So I wouldn't be surprised if in that point in the future we actually be close to this estimate here than this one. The other thing that we're still trying to figure out how to model better are the ice sheet models. As I mentioned before, ice sheets were the latest one to be coupled to our climate systems. In fact, this latest IPCC report was the first one that included ice sheets on it. So this graph here is showing the Greenland ice sheet change in mass with time. The blue line shows the observations, and the little thin gray lines are showing different models. And except for, a few stray ones here, they're sort of predicting, the mass is going to decrease, but there is still a lot of range of uncertainty in that. And if you look at the Antarctic ice sheet, is even worse. There are models that are predicting a complete opposite trend to what it's being observed. So clearly we have lots to work on here, but I have to say ice is a very difficult thing to model. It doesn't behave as neatly as water or air. So it's really, really hard to model and also to understand the physics of ice. So that's why you have to be a little bit more careful with modeling ice sheets. Now, how do I fit in this? Well, as Tracy mentioned before, I'm very interested in the polar regions. I am particularly interested in the interactions between land ice, glaciers, and the ocean. And in special, I'm interested on those little guys here, the icebergs. So I use an coupled ocean sea ice model that's called NEMO. And NEMO recently also coupled an iceberg model into it. And what you're seeing here, those little points are little icebergs that are moving around my model. And the hotter the color here, the larger is the iceberg. And what you can see is not that they're moving around, but also that if you fix on a particular point there, you're going to see they are changing colors, which means that they are melting as they go, they move around. So again, I want to go back to your fond memories of your physics classes on high school. You usually start a problem with this. Consider a spherical cow in a vacuum. This is more or less what's happening with this new iceberg model, right? We have a spherical cow. And to translate that in terms of the model itself, the icebergs are in the model are considered cubes, which they are not. If you're seeing pictures of icebergs, they have a whole bunch of different shapes, right? In the model, the initial size of the iceberg is sort of a guess, because the process of breaking off icebergs from glacier is very unconstrained. We don't know exactly how that works yet. So we are just based on a statistical distribution of what we see in nature. So we know that smaller icebergs break off more frequently than the larger ones. So that's what we base ourselves to give the initial size of the iceberg in the model. And in the model, smaller icebergs are grouped into one particle and they move all together. So in the previous video that you saw, I told those were icebergs. In fact, those were particles that were being tracked on the model. For the larger icebergs, indeed, inside the particle, there was only one iceberg. But for the smaller icebergs, you have a whole bunch of little icebergs inside that particle, and they are moving together. And this is not what exactly happens in nature, because eventually those little icebergs will sort of disperse and will not move together as a one unit, right? But if you start looking into the model, let's say the cow is not so spherical, because we do have some clever things in there. The model moves with real physical forces that are seen in nature. So the icebergs will move according to ocean currents, with the winds, with the rotation of the earth will also influence where they're going, the drag force of sea ice. So this is all physical, and this is what is telling how the model should move. So we can pop up a head on our cow there. They melt, right? They deteriorate as they move around, and that's according to wave erosion. So when wave breaks on the face of the iceberg, it will sort of make a notch on the iceberg. So this is accounted for in the model. We also account for the difference in temperature of the iceberg and the ocean, and also the turbulence that is generated as the iceberg moves around the ocean will also help it melt. Icebergs also capsize, they turn around, and that's important because it will change the aspect ratio of the iceberg, and that will also determine how they will move and melt. And this is also represented in the iceberg model. So we can add some new feature there in our cow. We are getting closer to a real cow here. Icebergs also break into bits, and the model also is able to reproduce that. So we can add a tail on our cow. And what I am doing is I'm trying to make this cow look more like a cow and less like a balloon, right? So what I'm doing currently is changing how sea ice interacts with icebergs. So for heavy, thick sea ice packs, the iceberg will actually move within that sea ice pack, right? It cannot plow through the sea ice. Even if it's a considerably large iceberg for the northern hemisphere. In the southern hemisphere, you have pretty large icebergs that maybe are able to do that, but not here. So I improved this a little bit by locking the icebergs under heavy sea ice conditions. The other improvement is how the melt plume from the iceberg enters the ocean. Currently, this melt plume enters only on the ocean surface, which is not very realistic if you think about it, because icebergs can reach down to 300 meters of depth. So the melt plume can actually be coming from the bottom of the icebergs as well. So this is another improvement for the model. And another one that I'm planning to do is to insert nutrients into that melt plume, because that's how it happens in nature. Icebergs are formed from land ice, and land ice had contact with rocks and everything, and they carry with them micronutrients that are very important for primary production in the ocean. So what you're seeing here is a plume that is around this iceberg of little algae in the ocean that are just flourishing by the presence of this iceberg, because it is, as it melt, it will release these nutrients in the water. And that's another process that I'm going to include in the model, making my cow look a little bit more like a cow, less like a balloon. Now, do I could keep adding things, right, in my model, ad infinitum, but and make my cow look like a real cow like this. The question is, do I want to do that? And maybe you might think that that's a straightforward answer, yes. But we have a concept in modeling that is parsimony, and that says that you should have a model that is complex enough to answer your scientific question, but not more complex than that. And there are two main reasons why you have to take that into account. One of them is that by trying to make something very detailed, you might be inserting more uncertainty in your model than you should, right? So you're trying to introduce a whole lot of details that you're not sure how they work yet. So maybe you're going to get worse results than just keeping with your cartoon cow here. The other reason is that maybe you're not interested in the cow itself. You're interested in the milk that the cow will produce. So does it matter if the cow looks like this or like this? Not really, as long as they produce the same amount of milk, right? So what matters is, what is your question behind it? If you are not interested in the cow itself, then maybe having a very well-detailed model of your cow will not help you very much. It will just increase computational time, it might increase uncertainties, and won't give you any better results. So you always have to balance those aspects when considering models. All right, so I'm gonna stop talking because I'm sure I want to answer some questions. So I'm just going to leave the summary here for you if you wanna read. But that's what we saw today, and I'm also going to leave my email there. If you have any questions, feel free to contact me. And thank you very much for your attention.
Thank you so much. That was very interesting, and I loved the use of the cow model. That made it more relevant for those of us who don't do this on a daily basis like you do. And thank you for that clarification about what goes in a model. How complicated it should or could be. So thank you for that. So we have had a few questions come through. So I'm going to go to Slido first. So Teddy, if you wanted to bring up the question that we have on Slido, and that is, in the temperature models, how many models are there in an ensemble?
Right. So currently we have around 60 models in the CMIP 6 ensemble. So those are lots of models, and they're coming from different parts of the world, different research groups, which is also great.
Okay, super. Thank you. Okay, then there's a question on YouTube, and it is, models with nonlinear equations tend to be extremely sensitive to initial conditions. How have you addressed this problem?
Yes, this is the thing about the butterfly effect and chaos is that one little thing in the beginning, as you move forward with the model, it's going to grow, right? So exactly. The way to deal best with this, of course, is to have better initial conditions. This is the first straightforward answer. So getting better instruments with more accuracy to give you that robust initial condition, that's the best way to go. What you also can do is again put together an ensemble, but not of different models now. With the same model, you run the model multiple times with slightly different initial conditions, and then that will give you a range of uncertainty that you can show and say, if you change a little bit the initial conditions, here are the results. So things are likely to stay between those bounds here.
Mhm. Okay, thank you. Also, from the same individual asking a follow-up question, wanted to know, are you familiar with Forrester's world model described in the book Limits to Growth from the early 70s?
I'm not, and I'm curious about it.
Maybe some next reading for you, I guess. So that's
Yeah, let me
interesting.
write
Yeah.
it down.
So
Thank
Frank,
you.
who asked this question, maybe you wanted to send another follow-up if there's something in particular from her that you wanted to ask
Mhm.
Dr. Marini Marson about that. That would be great. So while we're waiting for some more questions to come through, I had a question, and this is not at all scientific, but I'm just interested because it's there's a lot that's gone into putting this model together. So perhaps, in your opinion, what was most surprising for you, or what was something that you really weren't prepared for in preparing this model?
For the iceberg model, it's really every time I put something new on it, it gives me something more to think about and some new ideas of how to improve those models. So it's interesting. One of the interesting and surprising things that I saw is that some icebergs were not following exactly the ocean circulation, which is what you expect. Some of them are doing some weird things, but they that are also happening in nature. So that's also very interesting for us to really investigate closely to see what is going on there.
Okay, wonderful. All right, so we're still waiting for some more questions. So as we're doing that, can you speak a little bit about sort of what's next for you in your research, whether it's continuing down this path in terms of your modeling, or if there's something else that you're looking at, another model altogether, or combining a few others? What's next for you?
Yeah, of course. Of course, I mentioned that the iceberg model, but I also am working with the ocean model itself.
Mm.
In that sense, I'm not necessarily changing anything in the model. What I do is more run my simulations to understand how the ocean works, and through that, we can then improve the models. That's one thing. The other, of course, I'm going to keep going with the iceberg model, which I find fascinating. And the new thing that I'm planning to jump into now is actually coupling this ocean model with a glacier model, so I can actually study that interface between ice and ocean and how the feedbacks between them work.
Oh, interesting. And so, with all that work, do other climate scientists depend on your modeling work in order to do, like, what's your partnership like in terms of working with those who are on the ground, looking at changes in oceans and glaciers and whatnot and icebergs?
Sure. Yeah. Um, I chose to dedicate a lot of my time to icebergs because very few people do it.
Mm.
And so the improvements that I'm doing in this model is actually uh, it's spread to the community that once you use the model will get my improvements already in them if they want to run the model. Um, I actually am leading an international effort on the science of icebergs. And so we have some 150 members, more or less. and all of them are interested in some aspects of icebergs. A few of them are actually doing modeling with icebergs. So I guess my efforts go in this area really. So to advance the science of how we understand icebergs and how they affect the climate system.
Hmm. No, that's very interesting. Yeah, you're right. I don't think I've thought of it to that extent in terms of the role of icebergs in our climate system. So as we've been talking, a few more questions have come in. So Frank, who posted the previous point about that book, he's piped in with another point. So I wanted to bring that up on the screen from YouTube. And he says, I did a sensitivity analysis of this 5-equation model in my first paying job. The results discouraged me for pursuing the dream of modeling the world. Good luck with your work. So that's interesting. That was his experience.
Yeah, of course there are some things in models that are still need lots of work, and I'm more like on the side that I get very excited about that. It's like a problem to try and solve. So that's why I keep going with it.
Mm-hmm. Yeah, well, I'm glad you are. Okay, so two more questions have come through on Slido. So if Teddy, if you're able to put the first one up. And that is, that was a very intriguing talk. Thank you. My question is, what are the updated specifications of AR5 IPCC, and how does that differ from the previous ones?
Yeah, so the current one actually is AR6. That's the latest one.
Oh, AR6. Sorry. Okay.
Yeah. So if I had to summarize how the new report differs from the previous one, is that everything they were predicting that was bad is even worse.
Oh.
So sorry to say that. I try to keep my drawing of the cow in mind so you don't get too depressed. But yeah, that's essentially what the updated report is showing, that things are really going south for us, and now is the time to make changes. Otherwise, I in my opinion, we are unlikely to stay on the 1.5 degrees.
Right.
That was the Paris Agreement goal.
Mhm.
I think we are more likely to limit it to 2 degrees, but even then, we had to do some pretty serious efforts to reduce our emissions and mitigate them with time to actually maintain this lower level of warming.
Mm-hmm. Yes, some of your colleagues who've spoken in the weeks previous, we've been talking about this 1.5 degrees sort of, and not from a policy standpoint, but, well, I guess from a policy standpoint, but what is it that we can do as individuals in terms of contributing to that? So lots of discussion. So I'm looking forward to hearing what others have to say on that. So, okay, so more on Slido. So there's 2 more questions that have come up. Do you consider differences in salinity between the iceberg meltwater and the surrounding ocean?
Absolutely, that's very important. And as an oceanographer, that's actually my main interest, is how this freshwater plume that is coming out of the icebergs is going to affect the dynamics around the iceberg, right? So this might stir up the water around it, because fresh water that is coming out of the iceberg is very buoyant. It tends to go to the surface, while the ocean salty water is denser. So that creates some mixing in the water column, and that might also affect how the little algae or phytoplankton are able to do primary productivity, right, and grow. So that's one of my main concerns. Yes, we absolutely put the meltwater plume from the icebergs as a zero salinity water entering the ocean.
Okay, fascinating. Okay, the next question that's on Slido is wondering if there's a two-way use of knowledge between your research and the meteorologist monitoring Iceberg Alley, or is it just one way? Great question.
Yeah, and actually, I'm currently in conversation with the International Ice Patrol, which are the guys that actually monitor the Iceberg Alley. They hold the most of observations for the region there of the Newfoundland, and It's encouraging that my model results are actually reproducing well what they are observing in the real world. So we are looking forward to work together into developing better models so they also can forecast better iceberg positions and communicate them to ships and offshore structures.
Wonderful. I have been there in June to witness the icebergs. Everybody should go. They should have the
Oh
chance
my.
to see that. It's spectacular. It really is quite something. So, anyways, okay. Oh, another question has popped up through or comment through YouTube. It is, what is the greatest total distance that an iceberg has been tracked?
Hmm. In real life, that's a very good question. We have some trackers where the iceberg calved from the north portion of Greenland and went all the way down to, I want to say, let me look at my map here. I want to say like Hudson Strait. So before reaching the Grand Banks. So what usually happens if you're really lucky, those trackers can survive for most of the iceberg's life, but they might fail, and or the iceberg might break, and this will fall on the water and stop transmitting. So that's it's still a challenging
Mhm.
aspect of the observations.
But very interesting. That's really
Mhm.
interesting to see how far it does travel. Okay, so one more call out for questions. Anybody, if you wanted to ask on YouTube or Slido, we are coming to the end of our time. But if there's something else somebody wanted to ask, we can certainly make the time. Okay, so I'm not seeing anything. So thank you very much, everybody, for your questions. Thank you, Dr. Marini Marson. That was wonderful, very interesting. And I look forward to checking in with you a year or two from now in terms of where you are with your research and your modeling, and would love to learn more. To all of our viewers who are watching, we will be sending you a link to today's session and a survey where you can share your thoughts and your feedback. Please do respond. It's the only way we're able to improve. As you know, today is our final session of this climate series. It's been extremely successful. We hope you really enjoyed it. As I'm sure many of you know, Arctic climate science is a signature research area for the University of Manitoba, as you can clearly see by the expertise that we have shared with you over the last 6 weeks of the researchers who've presented. This topic was also selected because of all of you. Many of you mentioned in your feedback to us that you wanted to learn more about climate science. And so that is why we focused on this particular topic at this time. So I want you to know that your feedback does matter. We do listen and we do take action when we see the topics that you're interested in. So stay tuned for our fall 2020 program, where we're looking at some combination, some hybrid of an in-person and virtual. We do see the very important benefits of having this program run virtually, but also want to look at an in-person component for those of you who are in the Winnipeg area at the University of Manitoba. But also, as I mentioned earlier, please check out all of our content that we have on our YouTube channel from 2020 and 2021, and all of the sessions of this Arctic climate series. You won't want to miss it. Lots of great content. Thank you for participating, everyone, and have a great rest of your day.